Pharaoh is a city building game in which you cultivate an ancient Egyptian civilization. To attract skilled and wealthy citizens to your settlement, it's necessary to construct neighbourhoods with access to a variety of goods and services. Examples include a steady supply of food and water, access to healthcare and to religious facilities, and crucially, a local brewery. Whether or not a house has access to any one of these given services is determined by whether it's regularly visited by the associated worker. For example, a bazaar will distribute food to the surrounding area by sending out a trader, who will deliver food to any house she crosses. However, these workers don't travel purposefully. A bazaar trader will not deliberately seek out houses, nor will she avoid those to which she has already delivered food. Instead, she will execute something of a random walk around the road network connecting the bazaar to the houses. This stochastic behaviour means that junctions tend to decrease the efficacy of your workers. The greater the number of forks in the road, the greater the number of opportunities for the bazaar trader to get lost. She may end up missing a house, passing the same house twice, or walking into the industrial district. So let's say you have a bazaar, a house, and some network of roads in between the two. What's the probability of the trader reaching the house before she returns to the bazaar? In this video, we'll look at a particular family of road networks, namely a series of T-junctions, and see if we can come up with a general expression for the probability of the bazaar trader traversing it successfully. In the following we'll make two assumptions, which are not necessarily reflected in the actual mechanics of Pharaoh. 1. On reaching an n-way intersection, the trader chooses any one of the branches with equal probability 1 over n-1, with the exception of the branch from which she approached, which she chooses with probability 0. 2. The trader will wander forever until she reaches either the house or the bazaar, at which point she stops. Let's get started. First, consider a single road connecting the bazaar and the house, with a single three-way junction somewhere along its length. We will assume that nothing special lies at the end of the branching road, so that, when the trader reaches the end of it, she simply turns around and walks back towards the junction. For brevity, we will call the row segments before and after the junction 1 and 2 respectively, and the branching segment alpha, as shown on the board. The case of a single T-junction such as this is simple, in that the trader can only take a finite number of paths before stopping. Indeed, there are only 2 ways she can reach the house. Option 1. Walk along path 1 and reach the junction. Choose path 2 with probability 1/2. Walk along path 2 and reach the house. Or option 2. Walk along path 1 and reach the junction. Choose branch alpha with probability 1/2. Walk along alpha and reach a dead end. Walk back along alpha and reach the junction. Choose path 2 with probability 1/2. Walk along 2 and reach the house. These paths can be expressed in condensed notation as 1, 2 and 1 alpha 2. It's fairly easy to see that the total probability of the trader reaching a house blocked by one T-junction, which we'll call P of 1, is given by a half plus a half times a half, which equals 3/4. The first term is the probability of the trader going straight through the junction. The second term is the probability of her being diverted by the junction the first time, but choosing the correct path the second time she encounters it. A trader separated from a house by a single three-way junction thus has a 75% chance of successfully delivering food to it. Let's now consider a single road with 2 three-way junctions on it. The road segments are now called 1, 2 and 3, the branching segments alpha and beta. Some of the simplest paths that the trader can take are 1, 2, 3, 1 alpha 2, 3, 1, 2 beta 3, 1 alpha 2 beta 3, 1, 2 beta 2 alpha 2, 3, 1 alpha 2 beta 2 alpha 2, 3, and so on. We can now see things are, at least at first sight, substantially more complicated. With the introduction of this single additional junction, the trader is suddenly able to take infinitely many paths, because she can spend as much time as she likes moving back and forth between the 2 junctions, before finally committing to the road towards the house. But we're not going to let that deter us. Rather than writing out an exhaustive list of all possible routes in the manner above, it's actually quite easy to evaluate P of 2 by recycling our result for the single T-junction. we established that the total probability of a trader passing through a three-way junction was 3/4. For simplicity then, let's just replace our junctions with checkpoints that allow the trader to pass through with probability 3/4 and send her back with probability 1/4. What now are the possible simplified paths? The quickest route is to pass straight through both checkpoints, each with probability 3/4. The second quickest route is to pass through the first checkpoint with probability 3/4, be turned around by the second checkpoint with probability 1/4, be turned back around by the first checkpoint with probability 1/4, and then to pass through the second checkpoint with probability 3/4. For the third path, the trader is turned around 4 times, the fourth path 6 times, and so on. The total probability of her reaching the house is thus given by P of 2 equals 3/4 times 3/4, plus 3/4 times 1/4 squared times 3/4, plus 3/4 times 1/4 to the power 4 times 3/4, and so on, which we can rewrite as 3/4 squared times 1 plus 1/16 plus 1/16 squared, and so on. An infinite geometric series of the form 1 plus r squared plus r cubed, and so on till infinity, is well known to be equal to 1/1 minus r. Hence, P of 2 equals 9/16 times 1/1 minus 1/16, which simplifies to 3/5. So the trader's chances of reaching the house are slightly reduced by the introduction of the extra t-junction, from 75% to 60%. Let's go further and consider a triple t-junction. We won't bother writing out all the possible paths this time. We'll immediately play the same trick as before and make a super checkpoint around the first 2 junctions, which we have just established allows the trader to pass through with probability 3/5, and one around the third junction, which allows it to pass with probability 3/4. We'll now employ exactly the same logic as for the double t-junction. The probability of the trader passing through all 3 junctions reads P of 3 equals 3/5 times 3/4 plus 3/5 times 1/4 times 2/5 times 3/4 plus 3/5 times 1/4 squared times 2/5 squared times 3/4, and so on. Simplified, this reads P of 3 equals 3/5 times 3/4 times 1 plus 1/10 plus 1/10 squared, and so on to infinity. Using our expression for the infinite geometric series again, we can show that the above actually simplifies to P of 3 equals 1/2, or 50%. Now, you might have noticed a pattern is starting to unfold here. We've calculated that P of 1 equals 3/4, P of 2 equals 3/5, and P of 3 equals 1/2, which is 3/6. This progression is strongly suggestive of the following general expression: P of n equals 3/3 plus n. How can we prove this conjecture? We're going to use something called proof by induction. The proof starts by assuming that the probability of the trader passing through a series of n junctions is indeed 3/3 plus n. The first stage of the proof is to show that if this assumption is true, it necessarily follows that the probability of the trader passing through n plus 1 junctions is 3/3 plus n plus 1. This is the basis of proof by induction. We proceed as we have done in the last 2 cases. We form an uber checkpoint from the first n junctions, and a second checkpoint around the final n plus 1th junction. We'll need to use the fact that the probability of the trader passing through the uber junction is 3/3 plus n. So the probability of her being reversed by said checkpoint is 1 minus 3/3 plus n, which is n/3 plus n. On this basis, the probability of her passing through n plus 1 t-junctions is 3/3 plus n times 3/4, plus 3/3 plus n times 1/4 times n/3 plus n times 3/4, plus 3/3 plus n times 1/4 squared times n/3 plus n squared times 3/4, and so on. Factorising and evaluating the infinite series as before, we get P of n plus 1 is 3 over 3 plus n times 3/4 times 1 over 1 minus 1/4 times n over 3 plus n, and after a bit of simplification, we can show that the above is equal to 3 over 4 plus n, or in other words, 3 over 3 plus n plus 1. Bingo. With this result, we have shown that if p of 0 equals 1, p of 1 equals 3/4. If p of 1 equals 3/4, p of 2 equals 3/5. If p of 2 equals 3/5, p of 3 equals 3/6, and so on and so forth. The second and final step in the proof is to show that p of 0 is indeed 1. If we can do that, the probability of every other value of n follows automatically from our induction. Happily, the fact that p of 0 equals 1 is obviously true, because if there are 0 junctions between the trader and the house, she is guaranteed to reach the house. Therefore, we can state categorically that the probability of the trader reaching the house separated from the bazaar by n three-way junctions is indeed 3 over 3 plus n. Clearly, this result is just the tip of the iceberg. The road complex separating the bazaar from the house could contain many more interesting and complicated features, such as 4-way junctions, roadblocks, or loops. Here's a reasonably simple network for you to solve at home. Suppose the bazaar and the house are separated by a road containing a single loop. What's the probability of the trader reaching the house this time? Why not leave a comment or a video response and join the conversation? Thank you for watching.